Okay, we are back for the first physics talk of the school. It is my great pleasure to introduce you to you, Thia Keppel, Associate Director for Experimental Physics at the lab, former professor at Hampton University, friend and colleague of mine, and also former boss of mine. I can hear in part because she persuaded me to. And I stayed, so it was good for me. Thia will give you an overview of what we are doing here. So please go ahead.
Even better for us. So this is really great to see all of you guys. I actually love the HUGS program. I was a HUGS student sometime way back and a former HUGS director. And so it's really, really great to be a HUGS speaker. So this is fun. So I will apologize to you guys a little bit in advance in that as I was working, I modified my talk. I gave the HUGS lecture last year as well, the opening one. And I wanted to change it and modify it and add some new things and change how it went. And it got fully corrupted like about an hour ago. And so I freaked out. So anyway, a couple of my slides don't have text. So you have to pay extra close attention because I'll have to talk through the pictures. But I got all the pictures back up anyway. So I made progress. So hopefully this works. And maybe I'll try to make a version anyway that has the text for the Indigo for you guys to have that. Right on that. But hopefully it's not too bad. And just ask questions because that's what you're here for anyway, right? So it'll be good. We'll get there. All right. So starting very big picture. Why doesn't that go away? Will it go away eventually? Zoom stuff at the top?
No.
No, we can get rid of this.
Just maybe look at the chat. Maybe it's angry at that.
Oh, I see. Ah, magic. Okay, cool. All right. That's just going to keep happening if we get things in the chat. But okay, we'll see how it goes. At any rate, I kind of go back and forth between very broad brush, kind of maybe too simple for some of you, big picture what we're doing, and then some more detail. Like at the end, we'll be zipping along at 100 miles an hour. It's okay if you don't pick all that up and it's way too much. So just to try to hit everybody, because I know y'all are at a bunch of different levels. So we'll give that a go. So let's start super basic. I love this picture. It's pretty. So it's National Geographic and it's the birth and death of the universe going through time and all the different stages. And so where does Jlab sit in this picture of trying to study these giant cosmic questions? We sit both here and here, the first and second steps. And so you don't need to read this little tiny print. But at the very, very beginning, in the first sub-nanosecond of all of the universe, there's a little bit smaller than a golf ball size thing of everything. So you need the table, the building, the country, all the countries, the world, the universe, the sun, star, everything, right, is in this little golf ball. And this golf ball is full of quarks, kind of it, all right? And then quarks are a really strong repulsive force, right? And as this repulsive force takes over, this golf ball expands to eventually become the universe. But the first thing that it does is these quarks become protons and neutrons. And that's like in the first millisecond. So what we really want to look at Jefferson Lab are these two things: the fundamental structure of visible matter, so the quarks and gluons that make this up, but also the borderline of how these things form hadrons, mesons, nucleons, and nuclei, right? So not just the sort of structure so much of the quarks, but how matter is formed, that part. So that's where we sit, and that's our big overarching mission that maybe all of our entire experimental program maybe sits under those questions broadly. So that's where we are in the very, very big picture. All right, why am I not switching? Okay, I'll switch over here. Oh, I tried to click the slide. Yeah, it's because I did the thing. Yep. Okay. So how do we do that? You guys, I'm sure, probably have a picture for this, but I want to make a point that isn't always made. So typically we do the analogy of using Heisenberg uncertainty, or not even analogy, we deploy it and we say, okay, the distance that we want to probe is proportional to the wavelength of the probe that we're going to use, which is inversely proportional to the energy. And so that tells us that if I want to look at something super small, like a quark inside a nucleon, then I need to have something very high energy. So probably all of us as physicists have something like that picture. And we probably have another picture as well. We're thinking about, well, how do we see anything, right? How do I see this floor or this screen, right? My eyeball's not directly interacting with the floor or the screen, right? So, but photons are bouncing down from the light source, bouncing off of that, and bouncing into my eye. And my eye is a super sensitive photon detector. It tells me things like the wavelength, which I translate as color, the amount of photons I translate as intensity, all that. So that's how we see anything. So what are we going to do for any of these kind of experiments, right? We're going to go to very high energies. We're going to get a probe that we can deploy at very high energies. We're going to make detector systems like giant eyeballs, and we're going to start counting them, right? Counting the probes to get intensity, and we're going to start walking around it to get a feeling for shape and size. But the point that's not often made in that whole picture, which I'm guessing you guys all have a feeling for, it's the giant microscope picture, is why electrons, right? Why are there proton machines and electron machines, right? Jefferson Lab is the electron accelerator facility for the world. Why would you use electrons if what you want to answer is that cosmic question of what is the structure of visible matter, right? So you don't need to create new matter. So you don't need to do a proton anti-proton collision like you're at CERN or something, because there you're trying to create new forms of matter and study that. We want to study ordinary matter. How do protons and neutrons form nuclei? So why do you use electrons? Here it is. It's because they use the electromagnetic force and they're point-like, right? So two properties that make electrons perfect for doing this kind of science. They're point-like, so they're not going to modify what they're probing very much. They don't have the size of the probe, and besides being very high energy, but they themselves are point-like. The other thing is that we understand the electromagnetic interactions. So we can use that to get at any interactions we don't understand, like the strong force physics that we're trying to get at. So hence, you build an electron machine if what you want to do is study ordinary matter, because you want to probe something that you can just put there as a target. So that's what we do. Sorry, let me go backwards one more time. So this is a picture I'm sure you guys as physicists have seen many times. The going down in size commensurate with going up in energy being the same thing. But this is kind of a static picture. We have an atom and we have protons and neutrons inside, and we get down to the quarks, but that's a building block picture. And that building block picture is very, very, doesn't display the amazing dynamics that we have to take into account. So I just like to point out that these things are not static. They're really moving very quickly, right? So inside the nucleus, the protons and neutrons are moving roughly 3/4 the speed of light, right, in that tiny space. So they're zipping around, and they reside in a small space, but the quarks and gluons confined inside of any given proton or neutron are moving essentially the speed of light. So this is a very dynamic system. They're not building blocks at all. And in fact, it's this motion and energy that we're going to talk about that actually is the more important thing for understanding visible matter and the mass of things. So, okay, now here's my first slide where I lost all of my text. And it's terrible because there's so much meat to it. So now you guys have to pay intense attention to me because I don't have text. So now I'm gonna have to talk really slow. No, okay. We'll get there. Okay, so what I want to show you here is these two pictures. So I want to start with nucleons. And so we're gonna have quarks bound in the nucleus. Because remember in that very first slide, we had the two balls in the cosmic questions, right? The first one is that sub golf ball filled with quarks, right? So we're going to focus on the quarks initially. So this is the running coupling strong force coupling constant, which we call alpha S, not constant factor. So, and it changes. This is energy. So as we said just before, as the energy goes up, the distance scale goes down. Right. So this is the force between quarks. So it's a kind of a measure of the force between quarks. As I go out here, I'm going down in distance, right? And so the force is actually dropping to zero. So that's what we call asymptotic freedom. So remember this thing, right? As we're going closer and closer, the force is going to zero because we're going to go quite against that in a moment. And when you think about it, it's sort of surprising. So think about that for a moment. That's asymptotic freedom. What does that mean? It means that the quarks are free asymptotically, right, as they go close together. But then when they start to get pulled apart, so that's back here at lower energies, the force gets infinite. And in fact, it gets so big that as you pull the quarks further and further apart, rather than nature letting us have a free quark, if you get enough force in there, instead, what happens is this picture, this is a drawing by David Gross, is that the quarks pull and pull and pull, that the gluons that are binding them, it's kind of like, I'll go to an analogy in a moment, but they basically pull, they don't pull apart, they create new quarks that go and couple and pair with them and go on. So you get enough energy involved in that pulling them apart that energy creates more quarks. So you never get one quark out by itself. So at one level, we have this quarks are free. At this other level, they can never be alone. I don't know what happened there, but we'll worry about that in a minute. So these are the two kind of faces or manifestations of what we have for this nucleon structure. And yeah, so let me just leave it there. Hold those two in your mind while I talk about nuclei, because now we're going to have something really different. Here's nuclear force, because so now we're on that second circle in the cosmic questions. So here's the nuclear force. It's repulsive up here and attractive down here. And I apologize for that because we wanted attractive to be on the positive side, negative, positive, negative. But anyway, repulsive here and negative. So now, what do you have? This is the electrostatic Coulomb force. So think about protons and nucleus, protons positively charged, right? So you know, opposites attract, likes repel. So at some point, the protons, when you think that they're in the nucleus, why isn't the nucleus just blowing apart? Because it's got these two positive protons, right? They should be repelling and repelling and repelling because there's nothing else in there with charge. Yeah, but they don't do that. But that's what you would have from the electrostatic Coulomb force, right? That would be just, that's what we know. That's electromagnetism. Opposites attract, likes repel. But instead, we have this strong nuclear force as well, which does this thing. So this is a weird force. So as these things get closer and closer, it actually becomes infinitely repulsive there, yeah? And then they get further apart and it becomes quite strongly attractive. So these nucleons have a repulsive nature as they get further apart, an attractive nature as they get close, and then the force goes to zero again as they get further, and the force goes back to zero again as they get further. And in fact, eventually the Coulomb force takes over, and that's kind of the world that we're used to living in on a more macroscopic scale. All right, now think about everything. Now what I want to tell you is something that's puzzling and a part of why Jefferson Lab exists, right? Is that both of these things, this one and this one, are all the strong nuclear force. But wait a minute, what did I tell you? I said, when these quarks are super close together, they're free. And as you pull them apart, they're infinitely strong force binding them back together. And what did we just say about the nuclei, right? When the nuclei are close to each other, there's this near infinite repulsive force. Then there's an area where they're attractive, but then when they're farther apart, the force is zero. So how can that be the same force, right? It's exactly opposite in manifestation, but it's the same force going on, yeah? So except for this kind of dipping thing, but okay. Other than that, it's the same force. So that's quite strange what's happening there. And yet these are both the strong force, right? So strong nuclear force, strong force, binds quarks, binds protons, binds neutrons, all of these things are happening due to that. So what do we think is really happening is something like this, is you have within any given neutron or proton, these quarks are bound together and they're obeying the rules of asymptotic freedom. And as they get further away, they're infinitely bound or enough to create what? Create new quarks. And so the new quarks get created in those pairs because you can never have one by itself. And you get these mesons. And now what's happening is that same force that created those, these mesons are actually mediating the force between the protons and neutrons. And that's how you get the same force that's giving you two drastically different manifestations, right? So this is how we picture both the quarks bound in the nucleon, the nuclei bound together, how those things are interacting, all from kind of one picture. That's our current thinking. I'm going to guarantee that something I told you in there is somehow wrong, okay? Because you're going to figure it out 10 years from now. Because we don't actually know how all of that works really well. And we don't know a bunch of things, like we don't know why we can't have, why we don't have 5 quarks, like one of these guys living with one of these, or we kind of do, but only for a little bit, or why don't we have glue balls and things like that. There's a whole bunch of things we don't understand, which our current thinking would allow. But this is the picture that we have right now. And this is what the kind of thing that Jefferson Lab's job is to elucidate, say how big these forces are, how large these radii are, what kinds of new structures we can make out of these, all of that. In the big picture, that's what we're trying to do. Yeah.
Sorry, could you elaborate the contrasting manifestations of the
Sure. Yes, yes, yes. So here we go. So this is 2 quarks or 3 quarks, right? There's a couple quarks, yeah. And so these guys, when they get close together, there's essentially no force. They're free, right? And then they start to go apart, and they get infinite force pushing them back together. Yeah, that's 2 quarks in the nucleon. Then in the nucleus, what happens? In the nucleus, you have 2 forces because you also have the Coulomb force coming in. It's there between the quarks, but it's tiny. So in the nucleus, just look at the strong nuclear force part here. Completely different. As these guys get close together, they don't get free, right? They in fact experience a near infinite repulsion. And then as they get far away, unlike the incredibly strong pull back, they get 0 force. And then in between, on top of all that, in between, there's an attraction that isn't even, that it's not there in the other picture. So they're vastly different manifestations of exactly the same underlying phenomenon, we think. Okay. So far. Yeah, so very, very strong and hard to really get exactly from one to the other. And this is the picture that we have right now of how to move about from one to the other. But again, I don't know what it is. I wish I did, but I told you something wrong. Okay. So well, you guys will tell us. All right, so how do we know all this? And what we do know is that we've had success. We've been using leptons are, of course, electrons, but also neutrinos and muons. A powerful tool for studying nuclear structure for all the reasons I told you before. It's point-like, it uses electromagnetic interaction. We've been doing this for decades now. Not here at Jefferson Lab for decades. We as a nuclear physics community have. So it's a clean probe. We can vary the wavelength in a controlled way. You only get the electromagnetic interaction, so that's helpful. But there are challenges. The interactions are weak, which means you tend to have very small cross sections. Not weak like weak nuclear force, just not strong. They are small. This means that you have to have a large intensity machine. You'd also like to do coincidence measurements to see what else comes out besides just the scattered electron. And so because you'd like to do all that, and because there's lots we still don't know, we have Jefferson Lab. So this is a kind of overview. This single program was true until about a year ago. We're actually now allowed to expand out. So that's kind of exciting. You'll hear some about advanced computing, I think, and other things as you're around for these few weeks. But we have been in operation since -- we use the Continuous Electron Beam Accelerator facility. That's what we call our accelerator. So it's CBAF at Jefferson Lab. And it runs around below the ground. This kind of structure here. There's 2 linear accelerators, one over here and one over here. And so rather than go many miles around, we actually have a racetrack structure where the electrons are accelerated in a linear accelerator, brought around, accelerated again, brought around, accelerated again, brought around like that 5.5 times. So it sits on top of itself rather than being as large as if you were to spread that out. Our mission, as I said, is we want to understand the structure of matter through fundamental research and then also to advance accelerator nuclear science technology. And I'll say one slide about that near the end if I have time. So we have the largest nuclear physics community in the world, and it's still growing. We have about 700 employees, including 27 joint faculty or joint and bridge faculty. These are people who have positions at universities as well. We have about 170-acre site, about 1,700 active users. These users actually come from 39 countries and 278 institutions. So it's a broad worldwide physics community. And we also work with K through 12 programs, so younger students and teachers, and grant about 1/3 of the US PhDs nationally come from here. US PhDs in nuclear physics come from Jefferson Lab, come from an experiment or theory work done at Jefferson Lab. So broad brush, that's our site. That's what we're doing. Here's the same picture. I'm trying to give you a better feeling what I was saying about a linear accelerator around, accelerator around, accelerator around, like that. All this stuff is under the ground. And then the beam can go, so initially it is injected. So we have an injector, where we get the electrons from, and I guess you'll get an accelerator talk, so you'll hear about this, but more or less you kind of bubble them off of anything, right? Because there's electrons in anything. And so if you can put a high voltage to a conductor, electrons will become close to free and you can pull them off and move them on. It's not all that simple, and our injector people are really, really good, and they do a lot of amazing things to polarize the beam and things like that. But there's an injector. This is the first source of the electrons. Then they go through these linear accelerator regions. Through the world's largest helium refrigerator, because we're a fully superconducting accelerator facility, and so like a lot of cryogenic engineering going on. And then we recirculate, as I said, recirculate the beam. So as you can imagine, the electron beam coming through on first pass has a very different energy from the electron beam coming in on fifth pass. So these magnets need to be different for each of those passes. So each of these layers is a kind of a different, it is definitely a different magnetic path, and it's associated with a particular energy. And then there's 4 experimental halls, 1, 2, 3, 4, where we actually, this is where the user community mostly works, is in designing and running the experiments that exist in the halls. And so this is just a better photo of what's inside the halls. I'll talk a little bit more about the physics contrast. What I can say is, although this kind of gives a feeling what is the main physics program in each of the halls, what I would say is that each hall has somewhat different equipment, and we need to do that. So you'd say, why do you have 4 halls? Why do you have redundancy like that? And actually they're different. So you can imagine an experiment where what you want to see is really carefully electron in, electron out, and map that out with the highest precision you possibly can. Right? In that case, you really want to control, for instance, the focusing, the optics, the magnetic fields, everything involved in making sure you understand the incoming and outgoing electron. Was it an electron? Was it something else? What exactly was its energy? All those things. You're trying to focus in on that. That's what's kind of done in halls A and C. And another kind of experiment, maybe what you want to do is look at everything that comes out. So now you're going to have to sacrifice precision, right? Because you're trying to look at everything, so you can't be all things to all people, right? And so if you want to know if that was an electron or a pion, or if that was a pion or a kaon, or if that was a proton or a pion, then all those kind of particle ID detectors means that you're not focusing in on just that electron to get it perfectly, right? So you build a big onion and you put your detector in the center of the onion, and each layer of the onion is a different detector. And that's what's kind of done in Hall B and Hall D, except Hall D is particularly tuned to have a photon beam coming in. And then the difference between A and C is that Hall A actually has multiple experiments that we put on and take off the floor. So we put new equipment in. So we have to do all of those things. So you need 4 experimental halls. Or 6, no, you need more at least, to do all the science we want to do. Also to serve this large user community. So these are particle detectors. Broad brush, any one of these things weighs about 1,000 tons. So that's more or less the same as about like 5 747s or something like that. So they're very large pieces of equipment. But basically they're particle detectors. And I like to use this analogy, like you're looking at a water wave, and if you look at a water wave and you look at the height of the wave and the width of the wave and how fast they're going away and how fast they're going on, it gives you information about the ship that created them, right? This aircraft carrier, you're in Hampton Roads, so aircraft carriers are around here, it will give a big old wake, right? That's going to go on, and you don't want to get your little boat caught in the wake behind it, right? And then you go, oh, that was a big boat that went by, right? Whereas this guy's not going to be in the hard part of it, yeah? So at any rate, we look at the paths of the particles. We don't typically trap the particles. They go on out into the shielding, which is why all those experimental halls were under the ground, right? Just like the accelerator here. All right, so PAC approved experiments. We generally put them in broad brush into these 6 topics here. And then here's our 4 halls, and this is the number of experiments in each hall. And so we've completed now about 32 experiments. This, I should say, is in the what we call the 12 jet era. About 5, 6 years ago, our laboratory doubled our energy to go to 12 GeV as for the electron energy. And so people came and proposed experiments for 12 GeV. So we've completed about 32.2 of them, and we have about 52.3 remaining. And our program advisory committee that gives a science rating and approves or disapproves experiments that are proposed for the laboratory meets annually. So this number, it's not like we're going to go click, 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 and get rid of that and then we're done, right? Because our user community is brilliant and they keep thinking of new things to do, new questions to answer. But this is where we are at the moment to give you a feeling for that. And if you look over here, you'll see things like, as I was saying, we don't, questions that we still have, the three-dimensional structure of hadrons. So not only, again, not just a building block picture like there's 3 quarks and a proton or something, because there's more than 3 quarks, but also, and they're moving really fast, but can you get a picture of their three-dimensional structure? Like, how are they moving? Where are they moving? Are they moving around the outside, inside? What's going on, right? Do they cause changes in the proton structure as it's dynamically moving? All those things sits in the 3D structure. That's very different from hadrons and cold nuclear matter, which is more about how do these protons and neutrons make up nuclei. Right, and so there's, we divide them that way. And you'll see that pretty much we're evenly split amongst all these questions. So what I thought I would do for most of my talk, there's not a thing in here. So, a clock thing.
There used to be one.
There used to be, I know, that's why I keep doing this. So you're wondering, like, we're all doing that. There was a clock here.
So
You're good. So
you're at the half-hour mark.
good. Okay, that's probably perfect. So what I'm going to do is do 2 things. I'm going to show you a couple of experiments that are running in a little more detail, and then we're just going to zip through a smattering of other ones, so you just get a kind of a feeling and see some things, and it'll give you a feeling for the magnitude of the effort, I hope, because there is not time to talk about the science at Jefferson Lab, because there's 52 experiments, right? And I could talk for an hour at least on each one of those experiments, and you guys would be really sick of me. So we're not going to do that. So I picked 2 ones that are running right now to give you a feeling for those experiments and how they link together. And then I'll kind of whoosh through the program that's running at the moment. So this is nice because I chose this one in part because it's running, and in part because it hits those 2 circles and the big cosmic questions, and the thing I told you about linking how quantum chromodynamics is going to link both nucleon and nuclear structure a bit. So in Hall A, we're running an experiment to look for the neutron form factor. So if you think about the neutron form factor, a form factor tells you what? It tells you the charge distribution. Yeah, and so you can tell me, well, neutrons are neutral. They probably don't have a charge distribution, right? That seems weird, but the answer is that they do have a charge distribution. And so it looks something like this, where this is the radius. And remember from those pictures before about the size of distance between nucleons, the size of the nucleon, right? You're going to look for that sort of equilibrium position amongst all the forces that go on. So at its radius, we're neutral. But it does have this interesting positive negative structure to it. And these are experiments that have been measuring this form factor, and they come up with this positive negative structure. And what is that? That is actually the fact that sometimes the neutron becomes a proton and a pi minus. And this is the picture, whereas proton's positive and pi minus is negative. Yes, we have a positive negative structure. And so it can fluctuate. That neutron can become a proton pi minus, go back to being a neutron. And it can do that. And because of why? Because those quarks are dynamic, right? And so that's the picture that we had, where you're maybe exchanging the pions is the force that bonds and causes the interactions between the protons and the neutrons that binds and makes up nuclei. So even a single neutron will do this, of course, if all of them do it. So this is the picture. So we would like to understand this better, measure it out to further momenta, muck around with what is the real number in here, things like that. So we want to measure the neutron form factor, very, very basic measurement for the neutron structure. So this is part of something called the Super Big Bite Spectrometer program in Hall A. So this is another aerial view of the lab. There are those 2 LINACs, and here are halls A, B, and C. And Hall A is pictured here. And this is nice. This is what I was hoping would give you a feeling for the magnitude of these experiments. This was before last year. There were 2 large focusing spectrometers in the hall. There's a person over here to give you a feeling for the size. And one of these is fully kind of parked, removed, pushed to the side, gone off the floor. And the other one is kind of pulled over. And all of this equipment, this was actually mid-installation, but this is called the super big bite spectrometer system. So it has two magnets, large detector systems that actually also fill in the gap between here, a second detector system here, a bunch of electronics and a beam pipe, all of these things. And so the staff and experimental the scientists and user community people here do things like this, right? We take down an entire large experiment, put another entire large experiment up in order to look at these measurements. And this is happening over the course of maybe 9 or 10 months, trying to do all this work. So engineers, technical staff, all of these people working together. These are large efforts to do these experiments. So this is a particularly large effort, but it is not the largest that we've done at all. So in this super big bite program, this is called the super big bite spectrometer. That's because it has a large opening here, relatively speaking, is dedicated to precision measurements of these form factors. And the other thing that we will do, so to get at the neutron form factor, we used a polarized helium-3 target, which we used in Hall C actually in 2020. So this is, like I said, we're doing these big efforts, moving things around. It turns out that helium-3, the gas, you can polarize. How would you polarize it? So first of all, you have a filled helium-3 cell. So if you follow me, there's a little glass cell going here. And we put this glass cell in the path of the beam. And then we can polarize this helium-3 by letting it go up here, and we run many lasers, a lot of laser power into the helium. And we heat it up so that it diffuses down and goes through here. And so we have polarized helium-3. It turns out that the part of the helium-3, the proton and neutron, cancel each other out in the polarization, created an essentially a polarized neutron target for yourself. So we want to measure the neutron form factor, particular charge form factor. So having polarized neutron target is a good thing to use. Right now, you can use your electron beam to scatter off of the neutron and look at where the electron beam goes based on the charge it encounters, but also it's polarized, right? So the angular dependence is going to give you information about the charge distribution. So this thing we used in Hall C, and now we've upgraded it to make it even bigger and better and handle more laser power. And we've moved it over into, we've moved it over into Hall A. So not only are we installing and building new equipment, we're also repurposing and upgrading old equipment. All of that to measure these form factors. And this is terrible. So I am very sorry. But I can walk you through this, but don't look sideways because it's not even got the whole things. Remember how I said my talk got disrupted? So this is another manifestation of that. But anyway, what I would have shown you is that we have, you have an electric and a magnetic form factor. So the charge distribution essentially and the magnetic distribution, so picking up the motion for the proton and the neutron. So that's 4 form factors you want to get. And so the SBS program will measure all 4 of them with the highest precision and to highest momentum transfer. So again, the smallest distance that's ever been done before. So that's what that experiment is aiming at doing. We did one of them, GMP already, and we're working on GEN now. Then we'll move to GEP and GMN. So we're moving along the form factors in this SBS program. And then we're going to switch to a beyond the standard model search. So we go all over the place in the halls, but that's what we're doing right now. Sorry that this isn't showing up, but what this would have showed you is just the reach and the reach kinematically. What is the momentum of this experiment, the reach and the precision. Okay. Which is relevant, what's going on in Hall C. So this is kind of nice. This is another way to use that. So if you think about the neutron sometimes being a proton and a pion, you can also think that the proton itself is also sometimes going to be a nucleon and a pion. And this is, you can prove this to yourself, but also leverage it. So suppose that you have that nucleon and that pion, and you bring the electron beam in, and you get the pion and the scattered electron, you measure them both. Right? And now you think about like a pool ball type experiment where you know the incoming electron energy really well. And now you measure the energy and momentum of the electron and the pion going out with particle ID to be sure you have an electron and pion, and you reconstruct exactly the energy here, right? So you have an elastic scattering event, right? This convinces you that you hit that pion that was in there, right? You've got a pion, and now you can use that as a kind of a pion target. And so we can measure the pion form factor as well. And it turns out that you want to do something called longitudinal transverse separation in order to actually get at the pion form factors, because what we want is part of this component. So the pion is exciting. It's a QCD laboratory because it is the simplest bound system. It's two quarks bound together. So if we can't describe two quarks, well, that's simplest, right? So hopefully we can, but anyway, going to 3 and 6 and 100 or something for nuclei is going to be harder. So we'd like to understand the pion well. However, there are no free pion targets in nature. So we have to do experiments like this where we get at a pion inside a nucleus, inside a nucleon is the only way that we can do that. So they're harder experimentally, albeit perhaps easier theoretically to describe. So it can be calculated exactly at very high momentum transfers. But what we do is, I said, we indirectly measure the pion form factor using the pion cloud of the proton. So this means that we have a proton target, electron coming in, electron going out, and we measure the pi plus neutron. The same way a neutron can be a proton pi minus, the proton can be a pi plus neutron. And so here's what the online results look like, for instance. So this is a clean separation of the neutron and the pion state. So you can actually see it in the missing mass that we're getting both of these things. So that's a further conviction that this is the right picture. This is just to show you that we're doing it in Hall C. This is a photo of Hall C and going out to high momentum and high precision. And we will also do this for the kaons. So periodically there's a kaon in the nucleon as well. And that's fascinating because the kaon has a strange force. Right, a strange quark, sorry, it has a strange quark in it. And so that means that some part of the time as that proton or neutron are fluctuating into a nucleon and a meson, sometimes there's strange quarks involved in that. So they're heavier. So you want to think of the proton as being, say, a UUD, right? But it's not only a UUD, right? It's a very dynamic system. It's a UUD plus an S and an S bar and some other stuff. And so sometimes you can actually get that kaon that's created from that SS bar. This is a very important measurement. Another way, just to give you, again, a feeling for what's going on, we have this picture, very static picture of the elementary particles and elementary forces. And if you think about the nucleon, we could say that the proton, for instance, is an up, up, down, but that would actually give you that the proton should weigh about 10 MeV. So this should be another clue that our static picture is not a good one. And also the proton spin, when we measure the spin, only about a quarter of it is carried by those up, up, down quarks. There's something else going on. The proton mass is closer to a GeV, 938 MeV or so. And it actually is coming from all of that dynamic motion, all of those pions and other things that are inside of there are generating all of that. And in fact, generating, therefore, remember, most of the mass of the known universe. So it's not like a Higgs mechanism for particle physicists in here, right? More than 90% of the mass is actually sitting in quantum thermodynamics from these dynamic interactions. This is actually from a talk that Craig Roberts gave, and I don't want to go into all of it, except it's flashy, but to say that now that we can make sort of practical, this is from a theorist, right? So difficult experimental pion and kaon targets, we can move beyond the proton to explore and explain an entirely different form of hadronic matter, the mesons, with which the universe would not exist because the mesons are going to be the component of that nuclear force. So from a nucleon picture, or from a quark picture, they're the simplest. There's two of them make up a meson. From a nuclear picture, they're carrying a nuclear force. And so what we want to get at is the balance between those things and understand both. It's nice that we can study pions. But that is just one component of the Jefferson Lab program. So I thought I would show you that because we're in, actually, when you go out to the halls, when you guys get a tour, that's what you're going to see being set up in halls A and C are those two experiments right now. But there's two other halls and there's other experiments proposed for A and C, looking at different things and related things. So this is a feeling, this is a look at the recent life of a hall. This is Hall D. This is experiments and runs up to 23. And again, this means in this 12 GeV era. So not since the beginning of Jefferson Lab, just in our recent era. So since 17. So multiple publications. Hall D is tagged photon beam. We actually send the electron beam through a diamond radiator, and that gives us polarized photons at about 9 GeV. And that's what this Hall is designed to do, is to look at particles created by interactions with those polarized photons. It's a hermetic spectrometer. That means it's an onion. Okay. So it's a fully, they're getting full acceptance. So all of the particles that come out of the interaction. And lots of statistics of photo production. So this is the experiments that are proposed for Hall D, the program advisory committee or PAC approved days, and percentage of where we are with how we're running this on. And so you see different things, you know, each of these are different experiments, sometimes a very different experimental collaboration coming in, changeover within the Hall, and we're clicking through and more things come in and putting those in the queue and moving along. So that's Hall D. Here's some recent results and data analysis in progress. Also to give you a feeling for the breadth of the program. This is an axion search. Axions are a kind of a dark matter candidate. So looking for axions. So this is actually gamma P goes to, and you can see over here, what they're looking for in the interaction. This would indicate that there was an exchange of an axion. What's happening. So axion searches to looking at these asymmetries over here. This is what Hall D was proposed for. What we're trying to do is look for things with, in particular, the difference between natural and unnatural parities. What we're looking for are exotic mesons. So we want things that are in principle allowed by QCD, but which we don't see. So what we see typically, right, are the UD or UDD, the protons and neutrons, or we see these mesons like pions. So they're either two quarks, or well, a quark and a quark pair of some kind, or they're three quarks. But you could have five, right? You've got these things combined, which we know happens virtually, like those experiments in ANC I told you about. But why don't you have like bound objects that just exist like that? Right, and so why not is a big question. So that's in part what this call is looking for, are these hybrid mesons and glue balls, objects simply composed of gluons or largely composed of gluons. Either one would be good. So they're going at that. Here's some other physics that they can do because they're tuned to look for produced particles, specific particles. Remember, it's that big hermetic detector. They can, for instance, look for the J psi. So this is the photon coming into the proton going out, and the J psi. So the J psi, just like I told you when we produce kaons, that's kind of exciting because that means it's a strange quark, right? The J psi comes from the charm quark. So this is actually even a step further in looking at what happens in this interaction inside the nucleons, creating these new particles as part of ordinary matter. So this is J psi. They're going to continue to do that, building new detectors for calorimeter, transition radiation detectors, up our game in doing this to higher precision. And then something completely different, right? So you've seen exotic mesons, you've seen axion searches, you've seen J psi production, and this is looking at more conventional nuclear physics. This is looking for short-range correlations for the first time using a photon beam. And here, what we're looking at is nuclei, so big nuclei, right? Carbon, something like that, not nucleons, nuclei. And as we said, it's very dynamic. These nucleons are moving around 3/4 the speed of light, something like that. And so at some point they're going very, very high momentum. Yeah. And those very high momenta come from what we call short-range correlations. So that's when the nucleons in the nuclei are very close to each other. So they're interacting very strongly. They're moving very fast. And so we want to look at that and map that out. So they're doing that. So nuclear physics. So I like this because it's giving you all these different questions, different kinds of things that we can use by changing this equipment up somewhat, right? Not a small effort, but it's kind of a vast amount of questions our user community can ask that we can handle in these halls. Yes. No kinematic fit. So yeah, so what they're doing here for the short-range correlation studies, I also have added in something called color transparency, which I didn't talk about, but that's what it's speaking to. The color transparency is basically, when a nucleon gets hit with the electron beam with very, very high momentum transfer, so it's got a lot of momentum transferred to it. Typical thing is it breaks apart. That's deep inelastic scattering, right? It just breaks apart. Sometimes not. Sometimes it holds together. And sometimes it not only holds together, but it makes its way out of the nucleus. So in order to both hold together and make its way out of the nucleus, it has to be a very, very teeny configuration that's very, very tightly bound, so it doesn't interact with all the other nucleons that makes it out. So that's called color transparency because the nucleus is transparent to it. So this has been observed in mesons and not in nucleons. So that's what they're trying to do. But the problem is you don't know what the basis is for that. Right, so if you don't fully know the momentum distribution, right, so therefore sort of the sizing of the nucleons, you could try to fit for that and compare it to something, but then you're comparing it to something you don't know exactly, right? So it's trying to get a baseline. Is that helpful? Okay. All right. So I only have 5 minutes, so I'm going to zip through a little bit more to just say that not only that, but Hall D, for example, is preparing for the next round of experiments. So we're going to continue to look for these hybrid mesons, and we need more detectors. So at the same time we're running these experiments and analyzing these experiments, we're also building detectors for the next group of experiments. So there's always a lot going on. And Hall C, I could do the same thing, but now I just talked about color transparency. So this is a color transparency experiment and a large momentum tail experiment as well. And then looking for something called the EMC effect, which I don't have time to talk about, and building more detectors, just like Hall D. So again, I just want to give you a feeling for the breadth of the program. Same thing in Hall B, but here they are really focused on looking at that three-dimensional structure that I touched on very early on when I showed the pack chart, where we don't want to just look at the static picture, but we actually want to understand at the same time both the charge and magnetic composition, but also the three-dimensional nature of that, so the momenta and the position. And both the transverse and longitudinal momenta, so a full picture of the nucleon. So that's going to take a lot of mapping out, and there's a broad program in Hall B designed to do that. They're also looking for heavy photons, which is a dark matter candidate search. So that's going on as well. Very neat equipment that sits right up just 2 millimeters from the beam, very tricky experimentally. And then also looking at nuclear effects. So looking for nuclei, doing things like those short range correlation studies. So again, the breadth of the program. Hall A is also doing parity violation experiments, which let you, for instance, measure the neutron radius, so not the charge radius, but the neutral radius of lead. This turns out to have a large impact on neutron stars and neutron star predictions. So this is actually one of our most cited papers from the era before 12 Jlab, which was the 6 Jlab, half the energy era, actually came from the astrophysics community, quoting the first neutron radius experiments from Jefferson lab. And doing the same thing for calcium, it turns out that we did both of these experiments now, and everybody thought that we had this kind of locked down from a theory standpoint, kind of understanding what predictions for the neutron radius for lead, and then you could use those theories and predict for calcium, and it turns out that they're not that. So we have a bit of a mystery going on there, but that's very new results. And then the last thing I wanted to say, and then I'll wind up, is that Jefferson Lab, I've talked a lot about the core science, the structure of hadrons, but there's a lot of other things going on. We look at, we look for fundamental forces. We also, as I said, have bearing on nuclear astrophysics, some theory and computation, which hopefully you hear about lattice calculations and things like that. Accelerator science and technology, cryogenics. I told you, world's largest cylinder refrigerator. We've got lots of cryo engineers here. All of these things, and then other applications of all this technology. So one of my personal favorite side hobbies is medical instrumentation. This is just an example of what you can do with, for instance, the very basic workhorses of nuclear science, scintillators and photomultiplier tubes. This is a device that the technology moved out from Jefferson Lab to do this. This is a comparison of a mammogram, which is a breast x-ray. So basically it's leveraging the fact that tumors are a little denser than healthier tissue. So the x-ray can do just like a dental x-ray, right? X-ray beam detector goes through and your teeth cast a shadow because they're denser. So the tumors will cast a shadow because they're denser, but that's a structural picture and may not have all the information. Most of the tumors not much denser, right? Which is the case in this patient. There's not really a large density region. Another approach is what's called functional imaging, where there are certain substances which are preferentially taken up by tumors. In this case, it's a substance called sestamide, which works with the mitochondria of tumors. But at any rate, it's a different substance preferentially taken up by tumors. If you can also do the nuclear chemistry to put a radioactive label on that, then it's going to what? It's going to go to the tumor and it's going to sit there and emit radioactivity, which we can now detect and take an image. So that's a functional image, right? You're taking a picture of where is most of the sesame taken up. So that's what this is. And so it's very clear here where the tumor is. In fact, it's not where you would have guessed in this, as it turns out. So this device, this detector sits here, and we've moved on. We actually licensed this patented license this technology to a company, which was bought by a larger company, which was bought by a larger company. But meanwhile, so this is out there. They've sold many, many units. It's out there for patient imaging. But we thought we could use the same technology in the operating room, where if you've removed the physician has removed the tumor, put a detector over it to see if all the microscopic disease is gone that the surgeons can't see, try to detect it functionally. And then that was going well, but then they don't want this. So work on making wireless, and then they don't want to do this and look up at a computer screen, right? Because your patient's still sitting there in surgery. So we're trying to get imaging sitting on the, what we call the hockey puck, where's the detector that sits there. So this is an example. There's multiple projects like this. So there's more, right? a decade of 12 GeV experiments still ahead of us. We might be getting a positron beam as well as an electron beam. So positrons have all of the benefits that I just told you that an electron beam does, because it's just the antimatter partner of the electron. However, we'll get different, for instance, parity experiments, which are different manifestations. So it's another handle that we can use to understand nuclear structure. And we might upgrade our energy again. We went from 6 to 12, and we're looking at going maybe to 22. More new detectors, plus the electron ion collider, which I'm sure you're going to hear a lot about, is coming, and we're in charge of a part of the accelerator and the detector region are being built and designed here at Jlab. So I'm done. And I apologize for all the exciting experiments, which maybe some of you are students on, which I didn't get to talk about a lot. But Keppel at jlab.org, I'm pretty easy to find. Or actually, I'm not used to find some neat, but you can find. All right, thanks.
Now we are open for questions now. Please go ahead.
Yeah.
So the fire compactor, since the fire is not using a system, so it's not free, does it change the compactor compared to fire?
So that is, yeah, sure. So the question, it's a very good question, is if, because we're using these effective pion targets where the pion is part of a nucleon, is that the same as if we did have a free pion to study? So so the question is, hopefully, but we can check for it. And so the way that we can do that is to try to get as close to on shell as possible, right? So we want that real on shell pion. These are far off shell, right? They're virtual pions. So what we can do is look at the momentum dependence, the pion momentum dependence, right? And try to track that back to where it would be as close to zero, as low momentum as we can, right? And look at, do we have a significant change in that structure that we measure as we approach as close to the on shell as we can get experimentally. So that's what we do. So it's still an assumption that there's not some drastic change or something like that going right to on shell. We don't know that. We don't have a way, but we will, because there's actually an experiment coming on at CERN where they use pion beams. So they can measure, they don't have an electron, so we don't have an electron beam pion beam. That would be the ultimate experiment to do this. We don't have that, but they do have pion beams going through things. And so by bootstrapping between the real pion beams, the way that they measure the form factor and the way that we do, we think that we'll be able, as a broad nuclear physics community, we'll be able to get at that. But for our standpoint, what we do is we try to check the momentum dependence going back to the on shell. Helpful? It's a really good question. It's difficult. And we rely on our theorists to tell us that maybe we're close to on shell.
So kind of going off of that, I think when you had, is it kind of the similar reasoning for how they did the polarized neutron scattering? Because you're saying that it was the I forgot if it was like the spins of the protons that it
The cancel, that's right.
canceled
That's
out
right.
with each other. Because I know like I've seen stuff where they've done like, you know, deuteron scattering where they, you know, scatter off you know, the proton and the neutron simultaneously. So is this like elastic scattering where it's kind of like scattering off of the helium nucleus as a whole, or is this kind of getting it more to like a semi like deep and elastic where it's like going just off the neutron?
Yeah, so the way in actually the pion form factor and the neutron form factor, doing these elastic experiments is very helpful because kinematically we actually get the neutron going out. So and we know the incoming energy very well because we measure it. So we know the full energy. That's why like I liken it to a freshman physics like pool ball type you know, any kind of scattering basic experiment, because you know all the total energy coming in and you know the angles and energies going out. And you know that you only had those particles because you're detecting for everything. So you reconstruct the energy going back. So we call that elastic scattering. So we actually don't get the full thing because this neutron was sitting in its helium-3, right? So it's almost the same answer I'm going to give you is right, is we're going to detect that neutron and we're going to do this at various angles and momenta, right? And double check that it's not changing as we go lower and lower, basically, yeah. While of course changing the incoming electron beam momentum. So we have to do that because, and again, we have to rely on theory. We rely on the nuclear models of helium to tell us that this should be the case. In this case, it's expected that the polarized neutron approximates, the polarized neutron in helium-3 approximates a polarized neutron target. Not as well as we're assuming for the pion, actually. In this case, we're assuming we can get there to within like 6 or 7%. So they do have a big uncertainty on them. So we'd love to have a real polarized neutron target. And you could make them because there are neutrons in nature. The problem comes back to one of those other slides I showed you that these are small cross sections. So we also, maybe we can measure for a year, but we can't measure for 20 years. So we also need to have a lot of whatever target we put in place and a very high intensity electron beam. So there's kind of the practicalities of experimental life come in. Sure.
There is one for the back.
How long do you typically run like a single experiment for, and how much data do you get?
Yeah, so we run, this is, there's a big range. I think the shortest experiment that we've run is on the order of days, maybe 2 or 3. That's very unusual. I can think of actually only 2 in the course in 6 Jlab to 12 Jlab, but it happens. Long ones go on for years. So something like the experiment that I told you would go next in Hall A, the parity experiment that we'll do next, that's probably going to run for about 3 years.
And that's just like continuous?
24 hours a day. We run about 30 weeks out of the year, 24 hours a day. The rest of the time is down for switching over the experimental halls as well as for maintenance and upgrades to the accelerator. So we have a kind of a natural, you guys will be here probably when we start up near the end of your school, and then we'll start up and we'll keep running up until a winter break in December, and then we'll go again for maybe January and February for a bit, and then we'll shut down again into June. That's kind of our cycle.
Yes, this is more like a general question. So you talked about search of pentaquarks, okay? And Alice recently established that pentaquark exists in the charm sector, but not in the straight sector, using a specific confined set of quarks. So now when different experiments have almost overlapping motivations, like what is your take on how these experiments should collaborate with each other, collaboration across experiments?
So I actually, one of the things is, I believe, not just my take, but the physics community, if you find something super exciting like a pentaquark, right, well, you better go measure it, because he could have done in every best interest and attempt and everything, still something you didn't see that's not wrong, right? But, you know, that can happen. And so actually, the LHC pentaquark is still under scrutiny. But not scrutiny for a bad way, right? It's not anything bad. Like we all these are very hard experiments, not just at Jefferson Lab, but CERN everywhere. And so double checking is one of the things that this community does, especially for really hard stuff. So first of all, I think that is the spirit of cooperation, right? It's like, oh my gosh, that's very cool. We'll go try and see if we see it too, right? And we'll change quickly to try to do that too. So another thing about those program advisory committees, it's not in line like a train, like you propose first, you propose second, you propose third. So it's the order you're running in. No, we actually do it. Yeah, no, it can have scientific priority. So our searches for the pentaquark actually got pushed into line closer in order to hopefully help the community to look at what do we see. And then sometimes you can see something different about it than what they saw or something like that. So we begin to launch a new study. And then sometimes we just change order because it's experimentally expedient, right? Like this guy can run really well with this thing in this other hall, so we can do all the science together or something like that. So our scheduling is quite a complicated piece. So yeah, my personal take on how to go across the communities is to do as much interaction as you can, theory, experiment, different theories, work worldwide, because these are precious facilities. There's not many of them, there's a handful. And it's a huge effort to get any amount of this data out. And so sharing and discussing will help all of us do best. So many conferences and workshops, you know, and to try to talk to. Also, it's really hard to understand this stuff, right? So you need as much help as you can get to try to do that.
And this is also a special thing about Jlab. So you can design experiments to answer a specific question that comes up today. You design an experiment, you get it running, and so on and so forth. So you can do these things much more difficult at LHC.
Yeah.
Bigger collaboration, you have that machine there. So here we have this flexibility. It's a very complementary and very different kind of collaboration and environment that you work in compared to LHC or RIC. So it's a very special thing that we have here at Jefferson Lab. And oftentimes there are still human scale experiments. So where other students have a chance of doing next to everything.
Yeah.
So it's still special in today's things. There was one question there and another there. So
thank you. Thinking farther into the future, how do you think the focus of research here might change as the EIC starts to complement the research being done here?
Yeah, so the EIC, of course, is much higher energy. It is a tribute to electron scattering, right? This is way, but it's always going to be much higher energy and much lower luminosity. And that's just the nature of the machine. And so we're going to sit in this lower energy, higher luminosity space. So it turns out that that's what I would call the valence regime. So that is where you can best study the partons in the nucleon, the quarks in the nucleon that have that make up the quantum numbers of the nucleon, right? And so they happen to have the highest momentum in the nucleon typically. So that's the Bjorken X variable, for those of you familiar with that. So that high X valence regime, that's going to be Jlab territory always, I think, for two reasons. One is the cross sections are tiny, so you need high luminosity, and the other thing is that kinematically it is naturally where we sit. It's actually what the lab was tuned to do, and there's still lots of mystery there. The other thing I can say is that for other kinds of studies, like actually we work together on and things where you want to look at, say, the partonic structure, and what you really need is this whole big picture, right? You need not just the valence regime and low energy, you need to see how that links to the high energy regime and vice versa. You need to be able to go back because you're really looking at how things change across scale. You need both and maybe something in the middle like compass or something like that, right? You need information from multiple experiments and multiple kinematics. And so that will be another role Jefferson Lab will always have.
And you will know more about small x starting from not far from now. Last question.
Yeah, is there an agreed upon distinction between what falls under nuclear physics and what falls under particle physics?
That's an interesting question. It's a fun game. So, what kind of neutrinos are particle physics neutrinos? Neutrinos that come from an accelerator, right? If these are neutrinos from the sky that might be hundreds of GeV higher energy, they are nuclear neutrinos. So, so it's actually historical, and funding is the real answer, although it's funny. It's because what funding agency, like this is a nuclear physics funded laboratory, because a lot of what we're doing are these questions that involve nuclear physics. Obviously, a lot of what we're doing also involves particle physics, and particle physics now, physicists are talking a lot about quantum chromodynamics and looking at nucleon structure. So from a science community, maybe not so different in part. But there is also this other distinction, but it's sort of historically what was funded when, right? What this used to be super high energy physics, like way back 20 years ago, right? This is what particle physicists were doing, right? Now we move on. But it's also, I think, whether you're studying QCD, although particle physicists do some of that, but that's really nuclear physics regime. And then the other thing is if you're creating new particles, so if you're really trying to study standard model kinds of pictures and then the full pathway of mass and new particles, that's more particle physics. I would say, generally speaking, we're trying to understand the structure of ordinary matter.
But then it turns out that LHCb is producing tons of new particles, new hadrons and new whatnots. And so they're doing nuclear physics at this point that everything is mixed up.
Yeah. So scientifically, there's not so much of a difference, but.
Okay. Good. I'm happy that you're asking so many questions. We will be running a little bit late in the schedule, but that's what we're here for, to discuss on our stuff. Next thing, we will go out, well, we can grab something to drink also, but we go out also for a good picture. And after that, from our timetable, we should then come back at 3:45. I think it was written there for Matt's for Matt's lecture. We may allow ourselves 5 minutes or so time to come back and to go out and take a couple of pictures. Also, we don't have a professional photographer, so we may have a few hiccups along the way. But anyway, so 3:45-ish, we can come back and proceed and go from high to small x.